So we will now have, I will a little bit talk about how a computer algebra system works, and then we will go into analysis, and hopefully on Thursday the network here works and we will do the hands-on introduction. Okay, so yeah, here you see kind of a definition of computer algebra, and it says this is symbol processing plus numerics plus graphics. I mean, numerics and graphics, this is not anything really new for you. Numerics is just computation with numbers, and graphics, you all know what that is. But maybe symbol processing is the interesting thing we should talk about now. And this is calculating with symbols, variables, constants, function symbols, and so on. Yeah, as in mathematics lectures. So, yeah, computation with symbols. Okay. Now, we will in the following, during this semester, we will have symbolic mathematics and numerical mathematics. And yeah, so here we have a kind of a very rough comparison of these two approaches. So what is the advantage of symbol processing? I mean, I hear it says often, maybe I should say sometimes, the computational effort is smaller than with numerical computing. And also, and this is the real advantage, whenever you do symbol processing, symbolic computations, then you have general results. Yeah? For example, look at this example here. We want to know the limit for x towards infinity of this expression. And this expression is a function, and we have the first derivative of this function. And now we want to know what is the limit of the first derivative of this function for x towards infinity. Okay, I mean, we can do this computation. So we compute the first derivative of this, which is this. And now we take the limit for x towards infinity of this expression, and this is the limit of this towards infinity. And now we can neglect this plus 1 here. That's why we get here a 1 over x squared, and here we get the logarithm of x over x squared, because we can neglect this 1 here too. And now we see for x towards infinity, if we look at these two terms, we can neglect this one because it's much smaller for x towards infinity than this guy. So this one remains, that's what we have here. And now here we know that x squared grows much faster than the logarithm of x, and that's why the limit is 0. This was a symbolic computation. And because we did the symbolic computation, we get an exact result. So we know that the limit is 0. In contrast to this, we could do this numerically. What would that mean? What would you do? I mean, maybe if you could not calculate with the limit for x towards infinity, what could you do then alternatively, which would be kind of easier? Use a numeric value. Which numeric value would you use? 1. What does it mean? So you would use x equal 1 or what? No. But you said you would use 1. Oh, not the number 1, you would use one value. Which value? Or maybe you don't understand my question. I mean, what you could do, we want to know the behavior of this expression for x towards infinity. So that means we could use a very large number. So we could replace x by 1 million. Huh? And then look at the value. And we would get a pretty small value. Huh? Like, I don't know, 10 to the power minus 11, I would guess. Huh? But this is not 0. We could use an even bigger value, 1 billion, and we would get maybe 10 to the power minus 17, which is not 0 either. We would never get 0. So we could see we just compute a table of values. And from this table, we would see it looks like the values are getting smaller and smaller. But you never know. Infinity is something else. Infinity is not 1 billion. And it's not a trillion. It's different. So you never know. Yeah? It may eventually go towards infinity, even though it looks like it converges to 0. That's a big difference between numerics and symbolic computation. So whenever you can compute something symbolically, you have to, because then you have a hard result and you know the result. If you do numerics, you never know what happens beside the values that you computed. That's a big advantage of symbolic computations. Huh? Okay, now what is the disadvantage of symbolic computations? We would actually always compute everything symbolically because it is much better. But this method does in many cases not work. Huh? Many problems do have no symbolic solution. For example, let me give you an example. Suppose you're looking for a function f of x is equal to the indefinite integral of this function. No? There is no solution. There is no symbolic solution for this. That means there is no function whose derivative is e to the power minus t squared. There is no such function. You cannot write it symbolically. There is no chance to give a symbolic solution for this. But of course, the integral of this exists. No? Oh, sorry, this should be minus infinity to x. No? I mean, if you look at the picture, this is such a function. And the question is, what is the area under this function up to this point x? And of course this area exists, and you can numerically approximate this area, but you will never have the exact value. And even worse, the only thing you can do is, I mean, you can compute a table like x equal to minus 3 minus 2, minus 1, 0, 1, and so on. And you will get some values. And that's it. But there is no chance to to continue with symbolic calculations. I mean, how could you use this table and then apply it in some mathematical context? What is the limit of this table for x towards infinity? No chance. Yeah, and that's very important to know. Huh? I mean, when you will work as an engineer in a company, you will have some mathematical problem. So the first attempt should be try to find a symbolic solution. Huh? And only if you see, okay, I'm now extremely off-road and I have no chance to continue with symbolic calculations, then you switch to numeric computations, which is often enough. As soon as, for example, equations get nonlinear, you're off-road. Look at this equation. E to the power x is equal to the sine of x. It's a pretty simple equation. No chance to find a symbolic solution. No chance. Oh, yeah, I mean, yes, there is, oh no, no, there is no easy symbolic solution. How does it look like? It's like, and here we have 1, and it looks like that. And there are, of course, there are infinitely many solutions, infinitely many negative solutions. And yeah, I mean, for big negative values of x, the solutions are pretty close to the zeros of the sign, but they are of course not exactly at the zeros of the sign. So you have to do numerical computations. Yeah, and that's why as an engineer you have to be an expert in both. Okay, yeah. Here we have another nice example for a numerical calculation. We have this equation x squared equal to 5, and this equation has two roots, which are the square root of 5 and the negative square root of 5. Now, of course we can say we have x squared equal to 5. And then we can say x1 is equal to the square root of 5, and x2 is equal to minus the square root of 5. And this actually was an exact symbolic computation. Huh? And this is good. It's actually the best way to write this solution in this way. I mean, this is approximately 2.23 something. Yeah? But this result is much better than this. Why? Why is this better? Why is this better? Yes, this is the exact result. But I mean, I might say in all my applications, I don't need exact results. I just need it to, let's say, 6 decimal places. And that's enough for me. Because I'm never able to measure anything more exactly than 6 decimal places. But anyway, even then, this is better. This is better. Think of, suppose you have to do further calculations with this result. Why is then this better? Yeah, because the square of this guy is 5, and the square of this is something else. For example, if you have an equation, take this equation, x squared minus 5. If you use this result, then you get 0. If you use this, then this is not 0. Okay, maybe this is trivial, but it is important. Okay, and now the next question is, now we go to numerics. Now we say, okay, I am not happy with this because I have no idea how many meters this is. I mean, if there is the carpenter and the carpenter has maybe to construct this roof here, and then I tell him, okay, I need a piece of wood with square root of 5 meters. He will not be happy. He wants to know really how many meters and centimeters and millimeters this is, so he wants to know something like that. Now, how do I get square root of 5 to let's say 10 decimal places? And here what we can do is we take this equation, we divide it by x, and then we get this guy. And now we add an x on the left, which gives me 2x, and one on the right, which gives me this equation here. And now we divide this equation by 2, and that's what we get. We have this new equation. And this equation is for x not equal to 0, this equation is equivalent to this one. And now, what's nice with this equation, here we have an equation of the form x is equal to something. I mean, we call such an equation a fixed point equation. Why? Because it has the form x is equal to some function f of x. So we have an equation of the form x equal f of x with some function f, and you know this function f. F is 1/2 times x plus 5 over x. And now all solutions of this equation are called a fixed point of this function f. Why? Why do we call solutions of this equation a fixed point of f? Oh no, this is not a linear equation. What is linear in this equation? Look here, 5 over x, this is not linear. This is not a linear equation. And yeah, fixed points are not about linear equations.
The results are fixed point numbers, because we have to know the roots are square roots or something else.
Okay, yeah, that's a nice explanation. I've never heard this one. The result are fixed point numbers. You mean the result is a decimal number, or what? Yes, of course. The result is, but that's not the reason why it's called a fixed point equation. Suppose we have a solution of this equation, which we call x bar. X bar. And now we apply f to this solution x bar. What will be the result? X bar. The result is x bar. Why? Because it's a solution of this equation. And all solutions of this equation have the property that f applied to the solution is the solution. Okay, so now we apply this function f to some value x bar, and what does f do? It just reproduces this value x bar, and that's why x bar is a fixed point. It is fixed under the application of f, it reproduces itself. That's why it's a fixed point. Okay, so this is a fixed point equation. And now what we do is, we don't know the result. So we take any number and just put it into f. And look what comes out. And this one number to which I apply f maybe I'm very lucky and just use square root of 5. And then what will this function do? If we apply it to square root of 5, let's see, square root of 5 plus 5 divided by its square root. So this is the square root of 5 too. So we get 2 times square root of 5 divided by 2 is square root of 5. So you see, square root of 5 is a fixed point of this equation. It's being reproduced. And that's nice. So if we already know the fixed point and we just put it into f, we will get it. Question?
Isn't the second equation at this point equation 2?
Which second equation? This one?
Equals 5 over x.
Yes, you're right. This is a fixed point equation too.
Why did we need these 2 steps?
Oh, just because I like this one more. I mean, this looks a little bit more complicated, and that's why I like this. This is too easy. Yeah? I'll tell you later. That will cost us 4 weeks, and then you will know why this is better. Yeah. Now we just use this equation. The other one is not so nice. Okay, so if we put square root of 5 into this right-hand side, that means into this f, it's a fixed point. Now what happens if we take 0, for example? What do we get? Oh, this is not nice. Oh, this is not, no, we don't take 0. Huh? That's not a good idea. Let's take 5. Huh? And then this is 1 plus 5 is 6 divided by 2 is 3. So you see, 5 is not a fixed point of this equation. But we can just use it now. Let me see, what did we do? Oh, look, we used as a starting value not 5, we used 2. We put 2 into our equation. Where do we have it? Not here. And then we get, what do we get? 5 over 2, which is 2.5, plus 2 is 4.5, divided by 2 is 2.25. You see, that's what we get as the next value. And now we take this result and put it into my function again. And then this gives me this, and I repeat this. And what we get is finally a good approximation of square root of 5. So this function seems to have the property that no matter what you put in as an x, if you repeat this, if you iterate this, it seems to converge to square root of 5. Huh? This is numerical computation. And this is actually what your pocket calculator does. Your pocket calculator, whenever you compute the square root of something, it does, if you compute the square root of a, then it puts a here and iterates until it's exact enough. Okay. You can do this with many other functions. For example, a nice example which I used to exercise in high school was x equal the cosine of x. Anybody has a pocket calculator with a cosine key? Do you have a cosine key on this pocket calculator? Okay, so then take any x. Take x equal 1. And please put your calculator into the Bogenmaß. What is Bogenmaß? Radiant. Radiant modus. Yeah? But you can use the degree mode too. It works too. Yeah. Okay, so now take 1 and hit the cosine key. What do you get?
0.540.
Okay. Now hit it again.
The equal.
The cosine, not the equal, the cosine.
The cosine.
The cosine of the result.
0.857.
Okay, now hit the cosine again. You see, my old pocket calculator was much better. I only had to hit the cosine all the time. He has to hit cosine and the...
You have to write what you want to calculate.
Yeah, I know, this is these modern calculators. Yeah.
They had 2 bytes.
Yeah.
Yeah, 0654 now.
Okay, okay. And now hit it 20 times. Huh? You see the advantage of the old pocket calculators. Huh?
I got nothing in the
Oh, it's not important because it converges. What is the limit? Okay, you can all do it at home. And what?
0.73 something.
0.73 something. Yeah, and that's the fixed point of this equation. Huh? So that's numerics. You just hit the key of this function on your pocket calculator very often, and if you're lucky, not always, there are functions where it does not work. Huh? But if you're lucky, then you get the result. Okay, this is about numerics. We will go into this a little bit deeper in the future. Okay, but now, I mean, numerics on the computer, this is nothing new. You can use any programming language. You can use C or Fortran or Pascal, whatever. Yeah? Any programming language allows you to do computations with floating point numbers. Yeah? So numerics on the computer is boring. The interesting question is, how does symbolic computation on the computer work? I mean, today it does not work because I don't have a network connection here. But there are programs like Matematika or MATLAB or Reduce or Maxima, a couple of others, which really can do symbolic computation. So you put an equation, a symbolic equation, into the system, and then hopefully the system will give you a symbolic answer. How does that work? How is this implemented in the computer? Because basically the computer can do computations with numbers, but not with symbols. Okay, yeah, so let's look at how we humans do symbolic computation. When we talk about arithmetics, arithmetics is addition and multiplication of numbers. Then there are, this mathematics lecture might start with the Peano axioms. Peano was an Italian mathematician who first wrote down the axioms, so the basic laws of arithmetics. And these equations are some of the Peano axioms. They are not all, but some. I mean, this axiom, for example, is the commutativity of addition. Or this is about, what is that? This tells us that 0 is what? How would we call 0 in this commutative group of addition? Addition is a group, and 0 is the neutral element of this group. Or this equation is the associativity, and that means no matter how I put my brackets, as long as I only do addition, the result will always be the same. And there are some other equations, and from these equations all results in arithmetics can be derived by applying logical inference rules. I mean, that's what we do all the time. When you see a proof on the blackboard, this is nothing but applying logical inference rules to some basic axioms. Okay, so we humans can do symbolic mathematics. That's what you learn in mathematics lectures. And computers can do this too. Now, how do the computers do that? Let's look at an example again. So, we want to compute this expression. So we have the sine of the log x plus 2, and now we want to know the first derivative of this, yeah? Which is the cosine of ln x plus 2 times 1 over x, because this 1 over x is the inner derivative, yeah, of the natural logarithm of x. Okay, so now how would the computer do this? What we did, we can see it here. We applied the chain rule for differentiation to this expression. And this is the chain rule. The chain rule is it's a meta equation. Why is it a meta equation? Because here I have a function symbol, and here again. F is the outer function symbol, G is the inner function symbol, and then we have this variable x. And then this is the rule. So we first compute the outer derivative, and we just leave this g of x untouched, and then we multiply it with the inner derivative. That's the rule. And now, what have you done if you would have computed this? You would, of course, apply this rule to this expression. And how would you apply this rule to this expression? You would do pattern matching. I guess you might call it pattern matching. You would match this f with the sine, and you would match this g with... Yeah, look, this is not so easy. Would you match the g with the logarithm? I mean, if you would do it formally, you would match the g with log x plus 2. And then the next level function would be the plus. So you would actually identify this plus symbol with the function g. And that's what we want to teach our computer to do. Now look, our computer, of course, our computer only has an ASCII input language. So this is not allowed, this upper prime here. Yes, and also we would not allow such infix operators like plus. Why? Because the matching of the plus with this function g, maybe you even had the problem to match the plus with the g. So maybe it's better to write it in this form. The sine of, and then this plus operator applied to two arguments, ln x and 2. And on the result of this, we apply the sine. And now, you see, now you can do the pattern matching. You can match the sine with f. You can match the plus with g. Yeah. But unfortunately, the plus has two arguments. Yes, but okay, but I mean, yeah, it doesn't matter, because what we then do is we would apply the derivative to this operator plus, and we do have we know a rule for the derivative of a sum. How does that work? What is the rule for the derivative of a sum? The sum of the derivatives. Thank you. Yes. So that's actually what we applied here. So we do the derivative of the sine of plus. This is this outer derivative, f prime, and then this is just the outer derivative. And now here we have the derivative of plus of all the arguments. And now in the next step, here, from here to here, we just put the derivative in. That's what she said. It's the sum of the derivatives. Okay, and now you see we need the derivative of the logarithm, which is 1 over x, and the derivative of 2, which is 0, and then plus of 1 over x and 0 is 1 over x. And now we're actually finished, so we do a little bit of pretty printing, and that's the result. Okay, so now we have done it even more formally, and maybe we are now not so far from being able to give this problem to a computer. The computer needs to be able to apply such formal rules. So the computer needs to have a pattern matching mechanism. It needs to be able to distinguish between variables and constants. For example, this f here is a variable, a function variable, and this is a function constant. And in pattern matching, you always are applied to replace variables by constants, but not the other way around. You are not allowed to replace 5 by x, but you can always replace x by 5. Okay, so we need a pattern matching mechanism, and we need a way to write down such rules. And look, this rule, it has an arrow here. Actually, in a mathematics book, you would see here an equation sign. It's an equation. But here I put it with an arrow. That means we can only apply it from left to right. That makes it much easier for our computer, because the computer now knows it has to match the left-hand side of this rule with the left-hand side of my problem, and then apply the rule in this direction. If we would have the equality, then we may match this left-hand side with this. We may even match it with this and work in the wrong direction. That's why we have directed rules. And these rules are called term rewriting rules. And so what we need is a pattern matching mechanism, and we need a term rewriting system that can repeatedly apply such rewrite rules. Okay, yeah, so that's actually term rewriting. Yeah. I mean, when you have to implement such a system, you basically only have such a classical language like C. And using this language C, now the question is, how can we implement this pattern matching in C? Yeah, and I want to give you the idea of this too. Because the implementation of the pattern matching can be made quite easy. We need a tree representation of our function terms. Look at this term, the sine of plus, yeah, and then we use as a root symbol the sine, which is the function name, and this sine has one argument, which is plus. Plus has two arguments, which is the ln and the 2. Oh, I forgot, of course, something. What did I forget? I mean, let's put it here. This was the derivative, the prime. This is the top level operator. Then we have the sign, then we have plus, the ln, and here we get the x. And now it's important to distinguish between variables and constants again. So maybe we make it like that. We put a circle around the variables and a box around the constants. And now I have this tree structure, and now I look at my rule. My rule is a tree structure which is pretty similar. We have the derivative of f of g of x. Yeah. And now we have to match this tree with this tree. And this task is, I mean, yeah, this is the problem called subtree isomorphism. So we have to find an isomorphic subtree of this tree, a subtree of this tree which is isomorphic to this one, starting from the root. There may be here a big subtree. This might be whatever, let's say the tangent of something, a large tree below. That doesn't matter. Just the top part must match. If I can match the top of this tree with this tree, then I'm allowed to apply this rule, because here we have a variable, and this variable can be replaced by an arbitrary subtree. So the algorithms that do the pattern matching are like graph isomorphism. Yeah. And now how can I represent such trees in my language like C? I mean, I use lists. So I use pointers and lists of pointer structures, and I can represent arbitrary trees by using pointers in C. That's what so first you have to implement your data structure, your tree structure to represent functions, and then you implement a tree isomorphism algorithm, and then you can do all this in C. And finally, you will have built such a computer algebra system. It would actually be a nice exercise for any computer scientist to implement a tiny computer algebra system. Okay, yeah, and here we have examples of two systems, Matematika, Maple. They can do symbolic computation, and there are a couple of others, but the only ones that are really advanced and easy to apply are actually these two. I mean, MATLAB also has symbolic features, but these features are based on Maple. Yeah. Okay, so now we will skip this, of course, this introduction. We will do this next time when we have a network connection in this room. And then Richard will give you an introduction to Octave, which is the open source variant of MATLAB. Yeah, okay. And now we start with a little bit of analysis. Okay, and this is, I mean, this is a very fast and short repetition only. So it's up to you to look in your old books or scripts or find other books in the library and repeat if you have severe gaps in this area. Oh yes, and also let me mention that for the German students here, if you don't dare to speak English, ask your questions in German. That's no problem for me. Yeah. So I really want you to keep track with the lecture. So, and to the not German-speaking students, ask your questions. Ask your questions in English, and then I will know where I have to repeat something. Okay, so we start with sequences and conversions. What is a sequence? A sequence is a function from the natural numbers to the real numbers. So maybe this sounds a little bit abstract, but it's nothing but look at these examples. Look at this example. This is a sequence, 1, 1/2, 1/3, 1/4. So this sequence actually maps the natural numbers onto their inverses. It maps 4 to 1/4. This sequence maps 4 to its square. No, it maps, yeah, this is 2 to the power n minus 1. So it maps 1 to 1, 2 to 2, 3 to 4, and so on. Okay, and we use this notation. So, for example, this 1/n and then the parenthesis n in the natural numbers, that stands for the infinite sequence. This tells you where you have to take this n from. Okay, and now we can look at examples of sequences. Here we have a sequence 1, 2, 3, 5, 7, 11, 13. And now my question is, how does this continue? What is the next guy in this sequence? 25? 27? 31? I would agree with 29, yes. You know this, I mean the Germans, I'm sorry, I don't even know it in English. There is this game, ich sehe was, was du nicht siehst, und das ist grün. So, what's the name of this game in English? I don't even know the name in German. I spy with my little eye. I spy with my little eye. Oh, yeah, okay. And now, how do you... so, I spy with my little sequence. And the beginning of this sequence is this. Yeah? And you have to guess how it continues. That's a nice game. You can do it in, if you are in the evening in the discotheque with your friends. And yeah, it's really fun. It's really fun, yeah? Especially if you meet the girls there and they have no idea of mathematics, you can really impress them. And you know what? You can actually write, I mean, you know, now you said it's 29 the next. But I can tell you, oh no, it is 475. I can just do whatever I want. There is, of course, a sequence that starts with these numbers and then has 475 as the next. There is a sequence. But this leads too far. I will tell you at a certain point how you can construct any sequence. With any finite start, you can continue it however you like. So you can really fool these girls in the discotheque. You give them a beginning and they say some next number and you say, no, it continues with whatever you want. Okay, now let's use other examples. How about this one? 1, 3, 6, 10, and so on. How does this, what is the next? 78? Why? It's true, but why?
Plus 2, plus 3, plus 4,
Yeah.
plus 5. Plus
So the difference is all the time, here it is 2, 3, 4, 5, here it is 10, 11, and then 12, the difference. That's true. Yeah, that's how you can see this sequence, but you can also see, look, I mean, what he said is he gave me a recursion formula, a recursive formula. That means if I know the nth element of the sequence, his formula tells me how to get the n plus first element of the sequence. But now if I ask you a different question. What is element number 100 in this sequence? You know a way how to find it. You compute all numbers unto number 100. But the question is there a direct formula to find element number 100? There is an easy formula. Who knows it? What is element number 100? It is 5050. Why? Because these are the so-called triangle numbers. Huh? These are the triangle numbers, and the triangle numbers. What are the triangle numbers? These are the numbers, let's call them T of n, which are n times n plus 1 half. Huh? And this is nothing but the sum of I equal 1 to n of I. Huh? Is that correct? So if we take n equal 3, then we have 1 plus 2 plus 3 is 6. And we take 3 times 4 is 12, divided by 2 is 6. And you see, this is a formula for the triangle numbers. And the triangle number 100 is 100 times 101, which is 10,000 and 100, divided by 2 is 5050. Yeah. And why are these guys called triangle numbers? Where is there a triangle? Where is the triangle hidden here? Oh man, you should all know this. This is so nice and easy and basic. Look at this sum. You take the 1, and then you take the 2, and then you take the 3, and then you take the 4. Isn't this a triangle? Okay, let's continue with this guy here. So how does that continue? $146? No. 144. Yes. Why? Yes, the sum of the previous two. And what's the name of this sequence? Fibonacci, yes. This is the Fibonacci sequence. I could also tell you a story, but that would be too long, about rabbits that populate and... Now how about this guy here? I give you some more time. This is an exercise for you at home. Huh? Yeah, this is. Oh yeah, and look here. If you don't know don't find the results for these exercises, just go on to this website. This is the online encyclopedia of integer sequences. Huh? This is a web front end, and you can input the start of the sequence, and it will tell you how it continues. It will also tell you who invented this sequence, who published it, and give you all the details. But unfortunately, I put this sequence into this. It didn't find a continuation. So this is actually I invented this sequence. And therefore it's a nice exercise for you to find out how it continues. It's not too difficult. But this one, no, you can find this guy, but not this, I guess. They are pretty similar. Someone has an idea? Yeah, maybe we start with this one. I gave you a lot of numbers because this is quite sophisticated. Prime numbers? Is 10 a prime number? And 8 and so on? No. May I give you, I give you a hint, and you take it as an exercise with you too. Don't think of mathematics too much. Yeah, you need a little bit mathematics because it's numbers, but think of linguistics. You see, this is really the game for the parties, yeah? And you can invent so many new sequences. And also, I mean, there is a theorem which maybe I will prove it in the last lecture before Christmas, because then we can do some fun too. And there is a theorem saying that with any finite initial part of such a sequence, I can find any continuation. There is a sequence that continues with 1, with 2, with 3, with any number. And you can think of how to prove this theorem and find a constructive proof. A constructive proof means find an algorithm that produces a sequence that starts with any initial finite part. You can give any finite start of a sequence, and you will find an analytic description of this sequence. And that's nice. I mean, you can produce any sequence, however you want it to look like. Yeah, but I will give you this proof not before Christmas, because then we will have the right tools from analysis to produce such integer sequence. I mean, this is, it looks like it's number theory, but you can use results from analysis to produce any such sequence with any initial part of integers. Okay, yeah, that's fun, but that's what we do not need so often as an engineer. Now let's continue with engineering mathematics. We call a sequence bounded if there are two bounds, capital A and capital B, such that all elements are between A and B. We call a sequence monotonically increasing if for all n, a n plus 1 is greater than or equal to a n. So successive elements have to be greater than or equal, and then it's called monotonically increasing and decreasing if it's the other way around. And oh, we forgot the strictly monotonic. Sequence is strictly monotonic if we do have the greater here and not the greater or equal. Okay, and now there is a very important term, the convergence of a sequence. A sequence of real numbers converges to some limit a if and only if this formula holds. That means for all epsilon greater than 0, there exists a capital N which depends on epsilon such that the absolute value of an minus a is less than epsilon for all n greater than or equal to capital N of epsilon. Isn't that nice and elegant? Of course, if you see this for the first time, no chance to understand it. But you see it for the 257th time, I guess. Don't you? Who has never seen this? 2. And all the others, they are so smart. No, you know what? They just don't dare to be honest. Huh? Okay, so now let me give you a picture for this. This is the picture. Oh, but unfortunately, we need the picture and the formula. So I draw the picture. So now we do something that the real pure mathematicians, they don't like it. They never draw such a picture because this is maybe too applied, maybe too much of a picture, too less theory, I don't know. But you know, I'm a physicist, so I'm allowed to draw this picture. Okay, so we have this, let's put it here, A. And now to the right we draw n. And n is the integer index of our sequence. So we only have these discrete points. And here, this is the axis for our an. An is a real number, n is a natural number. And now we have some sequence. And now let's assume this sequence converges to this limit a. Okay? And now, intuitively, what would you understand if I say the sequence converges to the limit a? Of course, you would say it comes closer and closer to this value a for n towards infinity. So maybe if I would have asked you to write a formula, maybe you would have written the following, which is quite nice actually. You might have written limit of n towards infinity of an is equal to a. That's actually the formula for convergence. Yeah? So this equation says my sequence an converges to this value a for n towards infinity. But I mean, this is just syntax. It doesn't tell you anything about what happens. This is just our writing. Or let me say the following. This is a shorthand for saying my sequence converges. Nothing else. But it does not contain any semantics. So that doesn't help us. This is the formula. to look at. Because this really tells us what convergence means, and that's very important. You will need it in the future. When we do numerics, you really need this convergence stuff. Okay. So now, look at this picture again. So we want to say something like these values on this axis here, measured on this axis, are getting closer and closer to our limit A. And getting closer and closer, this more or less means the distance between my AN and A is getting smaller and smaller. And that's why we here have the absolute value of the difference AN minus A. Okay, so this is really obvious. And now, and here we say this absolute value is smaller than some epsilon. Okay, and smaller than some epsilon, this means that I can give any epsilon, let's take a small epsilon like this. So this is epsilon and this is epsilon 2. And now I get such a narrow ribbon around our limit. The width here is 2 epsilon. Okay? And you see this guy here is inside the ribbon. And that's why our sequence converges. Oh no! What if these guys go out of the ribbon down there? Then of course it does not converge. And that's why we of course have to require this holds for all n greater than or equal some critical n of epsilon. What is the critical n of epsilon? Of course this is not allowed. So it really has to continue. It may do something like that. This is our critical n. For all n greater than or equal to capital N of epsilon. For all these n, this distance to the limit is smaller than epsilon. But this is not all. A sequence converges if for every epsilon, this is the for all epsilon greater than 0, no matter how small this epsilon may be. I mean, talking about big epsilons is boring. We think about really small epsilon. No matter how small this epsilon is, no matter how tiny this epsilon may be, there is such a critical number n of epsilon such that to the right of this n, all elements of the sequence are in this ribbon. Okay? Now what happens if I take an even smaller epsilon like this? Yeah, what happens is I get this ribbon, which is much more narrow. And as you see here, so suppose it continues really inside here, then this is our critical n of epsilon. So you see this capital N of epsilon, it depends on epsilon. And that's why it's a function of epsilon. And if this holds, and that's very important, if this thing holds for all epsilon, no matter how tiny they are, then the sequence converges. And that's very, very important. Okay, and this is just a notation, what you have seen there. Okay. A sequence is called divergent if it's not convergent. Why are you laughing? Because that's so funny, divergent. Yeah, sometimes it's funny, sometimes it's not. Okay, let's look at examples. This sequence here converges to 0. This is, oh yeah, I mean, please prove as an exercise that this sequence converges to 0. Prove this by just applying this definition. It's not hard, but it's a really nice exercise because then maybe you understand the definition. And also you can prove that this converges to 1. Or that this is divergent. Yeah, proving this, let's think about proving this. How can we prove that this sequence, which alternates between 1 and -1, is not convergent? Yeah, okay, this is kind of challenging. No, let's make it easier. Let's prove that this sequence does not converge to 0. Because, why did I say 0 now? Because if you want to apply this definition, you need to know the limit a. If you have no idea of the limit a, what does then convergence mean? Convergence then means there exists some a, but you have no idea of what a I mean. So that's why I made it easier, and I asked you to prove that this sequence does not converge to 0. Why does it not converge to 0? Oh, that's very easy.
We use an epsilon less than 1, and then we don't find an n.
Yes, yes, perfect. If he uses an epsilon smaller than 1, for example 1/2, then in this ribbon with the width 2 times 1/2, there is not one single element of the sequence. So it can never converge, because for convergence we need infinitely many to the right of our capital N. So that's quite easy. This sequence is divergent, and I mean the proof here is the same as it is here. But please, at home, you prove that these two sequences converge. Yeah, and then we have some nice theorems. Let me look at, yeah, we have a little bit of time. I mean, today it was not my fault that we started like 20 minutes later. It was the fault of the Rechenzentrum. So you all go to the Rechenzentrum and tell them what happened here today. Yeah? They will be happy. Every convergent sequence is bounded. Yeah, so look at this picture before we think of the proof. The idea is the following. Look at this 2 epsilon ribbon. If I have found for this epsilon that it converges, yeah? So, and if the sequence converges, there is some epsilon. Now we take this epsilon, and we know that all infinitely many elements of the sequence to the right of this are inside the ribbon. Now how about these guys here? They may behave very badly. They may really jump out of this ribbon. But now how can we prove that the sequence is bounded? I mean, for this part, it's obvious. This is my lower bound and this is the upper bound. But how for the others here?
You take epsilon as the maximum value.
Excuse me?
You take epsilon as the maximum peak value.
Epsilon as the maximum.
Peak value. That one.
Yeah. No, we don't take epsilon as this value. No, I mean, but you're right. We look at this maximum peak value and we look at the minimum value here. And the point is that these are only finitely many. Maybe these are 100,000, but I mean there is a maximum in 100,000 numbers. And we just take the maximum, which is then the upper bound, and we take the minimum, which is the lower bound. But be careful, the maximum may be inside our ribbon. So if the maximum is inside the ribbon, we of course take this value as the upper bound. So that's the way how we get an upper and a lower bound if the sequence converges. Now, this is an even, for practical purposes, this theorem is even more interesting because it says every bounded monotonic sequence is convergent. This is really interesting in practice. In many cases, you can apply this theorem to prove that a sequence converges. What do you need to know? You need to know that it is bounded and that it is monotonic. And this implies that the sequence is convergent. Yeah, why is such a sequence convergent? Maybe it helps to look at this picture. I mean, we don't need the full formal proof, but the idea of the proof. Maybe you first think of a counterexample. How about we have a monotonic sequence, maybe even strictly monotonic, or monotonic, it doesn't matter. No? Suppose we have a monotonically increasing sequence, but no upper bound. What may happen then? Yeah, it may go to infinity and it's not convergent. But having an upper bound does not allow our sequence to go to infinity. Okay, so now assume we have a bounded sequence, but it's not monotonic. What may happen then?
Sometimes it will reach B, the bound.
It may reach the bound. Yes, but does that matter? I mean, the question is, you have to give me an example of a sequence that is bounded but not convergent. And I mean, if the sequence hits the bound or the limit, that doesn't matter. Huh? Give me an example of a sequence which is bounded but not convergent. The sign? Yeah, I mean, yeah, the sign is a real function. We talk about integers. So you take the sign of n of the integers. Not? You can do this, yeah? So if you take the sign of n, you get some erratic thing which looks like it somehow oscillates between -1 and 1. Yeah? And I mean, it's a good example because it is bounded between -1 and 1. But of course, it is not convergent. Does not converge at all because it oscillates. Yeah. Okay, and now if the sequence is bounded, and it is monotonic, and monotonic means it's either increasing or decreasing, but not both. I mean, it cannot switch between. So then this sequence either approaches the upper bound if it's monotonically increasing, or it approaches some bound which is smaller than the upper bound. This may happen too. Huh? But if it approaches the bound, then of course it's convergent. That's the intuition behind the proof. And also it's a nice exercise to write down the formal proof. Okay, so now let's look. Yeah, maybe we stop here. Okay.